Hi there. Welcome to this video, which is going to be a 100% walkthrough for the Chemistry IGCSE 2021 Paper 2 paper. Let's get started. First question says, name the element with atomic number 14. Remember, it's the bottom number for the elemental symbol, which represents the atomic number or number of protons found in the nucleus for that particular atom. That would be, in this case, silicon. Next question says, name the element with the relative atomic mass of 11. Now, in this particular example, the term relative atomic mass is being used interchangeably with the term mass number. So we're looking for the element with a mass number of 11. That's the top number for any particular elemental symbol. If you look along the periodic table, you'll find that that represents boron. Next question says, name the element in group 2 and period 3. So group number represents the number of outermost electrons found in the outermost shell for any particular atom, whereas period number represents the number of occupied electron shells with electrons occupying those particular energy levels. Looking for an element which is in group 2, so that would be, remember, groups are the vertical rows, that would be the second vertical row along, and then periods are the horizontal columns going across and they run down. So we're looking for the element which is group 2 is 2 across and then 3 down, as in 3 periods down, and that would be the element magnesium. Next, determine the number of neutrons in a phosphorus atom which has a mass number of 31. So mass number represents the number of protons and neutrons found in the nucleus of an atom, whereas the atomic number, the bottom number, only represents the number of protons. So if we take away the atomic number for phosphorus, 15, from its mass number, 31, what is left over will be its neutron number, which is 16. Next, it says state the electron configuration for an aluminium atom. So aluminium atoms have 2 electrons in the first shell, 8 electrons in the second shell, and 3 electrons in the third shell, 13 electrons total. So represent that with the following sequence: 2, 8, 3, 2 electrons in the first shell for aluminium, 8 in the second shell, and only 3 remaining in the outermost shell. Finally, so that's why neon is unreactive. Well, that's because neon is an example of a noble gas. Now, noble gases have full outer shells of electrons, or full valence shells of electrons. This means they have no tendency to gain or lose electrons, and therefore getting involved in chemical reactions, and therefore we would state that they are inert or unreactive. So it's a noble gas and has a full outer shell of electrons. Now, question 2 is investigating the process known as rusting of an iron nail. So a student has placed an iron nail in some water and left it for several days. The first question says, predict the appearance of the nail after those several days have passed. Well, the rusting process would have taken place. I'm expecting the grey metallic colour to have changed to a brown-orange flaky appearance as the rust has formed on the surface of the nail. So we've said a brown-orange flaky solid has appeared. Name the main compound that comprises rust. It's a very specific name here, guys. It isn't just iron oxide. We have to say specifically it is a form of iron oxide known as hydrated iron 3 oxide. The 3 telling us the charge of the iron ions in that compound are 3+ ions. It's iron Fe 3+ ions present in this compound. The student then sets up 2 more test tubes containing iron nails, as shown by the pictures here. One in board water with an oil layer above, and one with a drying agent present and no water at all. We have to then explain why the iron nail in tube 1 and the iron nail in tube 2 did not rust for various reasons. Let's look at tube 1 first of all. So in tube 1, we can see 2 things. We can see the board water is used. That's going to reduce the oxygen content of the water initially, because at higher temperature, less oxygen will remain dissolved in the water, because gases are less soluble in water at higher temperatures. So less oxygen will be present in the water at higher temperature. That should at least slow down the rate of rusting. And secondly, the layer of oil present is going to also help to create a physical barrier preventing contact between oxygen molecules and the iron nail. And there's no oxygen molecules coming into contact with the iron nail, there'll be no rusting taking place, because oxygen is necessary for the rusting process chemical reaction to occur. Now in the second tube, we have no water present. So in the second tube, it's the drying agent taking effect. In case there's no water present in tube 2, that means no rusting can take place, because both oxygen and water are necessary prerequisites for rusting. The drying agent is absorbing water and moisture from the air. And if there's no water, you can have no rusting, because again, as I said, water and oxygen must be present in the contact with iron for rusting to occur. Question 3 is looking at the process of fractional distillation and the separation of crude oil. The first part of the question says, give the name of the industrial equipment shown in the diagram above. This is known as the fractionating column for the fractional distillation process. Then asks us to think about a use of the fuel oil, or the fuel oil fraction. So fuel oil will be used for either shipping or for powering power station generators. It's a thick, viscous, gloopy, not particularly flammable, high boiling point fraction, but it does give out a lot of energy when it is combusted, and that is why it's used for such large scale transportation uses or the powering of generators. Give the name of fraction A and fraction F. Well, fraction A is coming out right at the top of the fractionating column here. Okay, that's going to be a very low boiling point fraction, highly volatile fraction. That is going to be either known as refinery gas or liquid petroleum gases. Whereas F is coming out right at the bottom. It's the polar opposite. It's going to be a very viscous, highly viscous, high boiling point, not very volatile fraction, and that's going to be known as either bitumen or residue, which is used for tarmacking roads. So fraction A is refinery gases or liquid petroleum gases used for cooking and heating purposes. That's like bottled gases in barbecues. And fraction F is known as residue or bitumen and is used for tarmacking roads. The next part of the question is talking about the alkanes, and it's asking us for the general formula of the alkanes. The general formula of the alkanes is CnH2n plus 2. What that means is, whatever number we place here, double that number and add 2, and we'll have the number of hydrogens in that particular hydrocarbon alkane molecule. And that's how the general formula works. And this general formula allows us to work out the formula of any alkane of any size. Then we're asked to explain in terms of the structure why C12H26 has a higher boiling point than C8H18. The most obvious thing to spot there is that it's a bigger molecule. So C12H26 is a larger molecule than C8H18. Therefore, it's going to form a greater number of weak intermolecular forces along its increased chain length proportionately compared to C8H18 molecules. So it's going to form greater number of weak intermolecular forces per molecule in C12H26 versus C8H18. And that will mean that more heat energy will be required to overcome that greater number of weak intermolecular forces, resulting in a higher boiling point as a result. The final part of the question is looking at the process of catalytic cracking. That's cracking using a catalyst. Now, cracking is often used to increase the number of short-chain molecules present. If fractionation hasn't got a large number of those and it's not meeting demand, we can use cracking to create a greater proportion of short-chain alkanes and alkenes to meet our demand, as those molecules tend to be more useful in nature. So we're being asked to figure out the name of the catalyst used in the process of catalytic cracking. Lots of options here. The one I often use is zeolite, which is the name of the catalyst, which is an aluminium silicate, but you're also allowed to use the term alumina, and silica are equally creditable. And then finally, we're being asked to complete the equation for this cracking reaction. And I'll show you the solution to this here. Okay, so first thing I did is I took away from the original alkane molecule the known formula of the cracked product we know we've made. So I've taken away the C9H20 molecule from the C12H26 molecule, which means I'm trying to account for what's left over, which leaves me with C3H6, which must therefore be the identity of the missing molecule in this arithmetic-based cracking reaction equation question. Okay guys, so question 4 is a solubility-based question. We've been given a table of data with temperatures and the mass of potassium nitrate in grams that is able to dissolve in 25 centimeters cubed of water at those varying temperatures. And it's been told that one of the results is likely to be anomalous in nature. First thing we're asked to do is to plot the results on a grid or on graph paper effectively. So you can see my ticks here is showing that I have, when I've done this plotting, I've made sure I've ticked off as I've used the data along my curve, and here is the data building up. I've then been asked to circle the most likely anomalous result. So I'm looking for a result that doesn't match the general pattern of the other points plotted. As you can see, I've got this lovely smooth curve of points plotted, but this one stood out to me as not matching that trend or pattern in the data, so I've circled that as the anomalous result. The final part of the question said, ignoring the anomalous result, draw a line of best fit, or in this case, a curve of best fit. So because my data was naturally curving away, I've just literally done, not dot to dot at all, this is just a smooth curve through the majority of data points, and I've not included the anomalous result as that was the instruction. So I've left the anomalous result unused and drawn a smooth curve through the majority of my data points. I definitely have not gone dot to dot, because that is not the way we construct a line or curve of best fit in chemistry. It's not dot to dot, it's either a straight line through the majority of data points or a smooth curve through the majority of the data points. So question B says, suggest two possible mistakes that could have caused the anomalous result on the previous graph. And I made note to myself saying the anomalous result was below or under the trend or pattern of the other results. So we've got to try and account for that or make note of that in our answer. So here are the two options I went with. Insufficient mass of potassium nitrate solid was actually added. We could have dissolved more. We just thought we'd finished and we should have carried on. The second one was that the solution either wasn't being stirred sufficiently or wasn't being stirred vigorously enough. So it would have dissolved if we carried on stirring, but we gave up too early, and so it appeared that it was coming out of solution, when in fact actually we could have dissolved more if we'd stirred more vigorously and mechanically dissolved the solid. The next part of the question says, use your graph on the previous slide to find the maximum mass of potassium nitrate that can be dissolved in 25 centimeters cubed water at 75 degrees centigrade. Show on your graph how you obtained your answer. Let me show you how you go about proving that answer. So you go to 75 degrees centigrade on your x-axis, you find where that point is, and you draw a line straight up from there all the way to the curve where it hits the curve. And then you draw a horizontal line across to see the corresponding value on the y-axis for the mass of potassium nitrate in grams that can dissolve at that particular temperature. What comes out is 40. So my answer there was 40 grams. And the final part of the question says, use your graph to calculate the solubility of potassium nitrate in grams per 100 grams of water at 25 degrees centigrade. Okay, so again, we can use our graph for this. So we go to 25 degrees centigrade and we find out that if we draw up directly from 25 degrees centigrade and then horizontally across, we get 11.5 grams of potassium nitrate being dissolved at 25 degrees centigrade. Remember, this is in 25 centimeters cubed of water. So what we're saying is in 25 centimeters cubed of water at 25 degrees centigrade, we can dissolve 11.5 grams. Now, 100 centimeters cubed of water, 100 centimeters cubed of water is 4 times that amount of water. So if we multiply the mass that dissolves in that volume of water by 4 as well to match the increase in the volume, we get 46 grams of potassium nitrate being possible to dissolve if we had 100 grams of water rather than 25 grams of water. So we're scaling up through a 4-fold increase in volume of water. Question 5 is an organic chemistry question looking at alcohols. Okay, and we're asked to give 2 characteristics of what a homologous series is. A homologous series is a family of molecules, but there's lots of ways we could define what a homologous series is. So these are 4 options to get your possible 2 marks. We could have said that homologous series has the same general formula, like CnH2n for alkenes, for example, or CnH2n plus 2 for alkanes, for example. They will have similar chemical properties because they contain the same functional group, which gives them their chemical properties. They'll have a graduated trend in their physical properties, a gradually changing physical property, like, for example, increasing boiling point as chain length increases. And each successive member of the family will increase in size by CH2. That creates the bigger, larger members of the family. We're then asked about more about ethanol in particular. So when ethanol is heated with potassium dichromate, an oxidizing agent, the ethanol is oxidized to ethanoic acid with the formula CH3COOH, which is the carboxylic acid functional group. Give the formula of the other reagent. Okay, so we need a sulfuric acid catalyst present to encourage the reaction to go to completion. So the other reagent is sulfuric acid, H2SO4, acidified potassium dichromate. We're then asked to state the colour change that occurs during that oxidation reaction. So what happens is the potassium dichromate, or sodium dichromate, in this case it's potassium dichromate, is a deep, bright orange colour. As the oxidation reaction progresses, we form chromium 3+ ions, and the colour of the solution changes from orange to green. So we're looking for an orange to green colour change to occur to evidence that an oxidation reaction has taken place and converted the ethanol into ethanoic acid. Next part of the question says, draw the displayed formulae for ethanol and ethanoic acid in the boxes provided below. So displayed formulae means we have to show all of the bonds present in the molecules, and that's what displayed formula is all about. So there are my 2 diagrams. Okay, so ethanol is an alcohol. So it's a 2-member alcohol. Eth stands for 2 carbons. So we've got a 2-carbon-based molecule with the OH functional group at the end, and that's all the bonds shown. Each carbon being tetravalent can form 4 bonds. And here is ethanoic acid. Again, eth, same as a 2-carbon-based molecule. First carbon 4 bonds shown. The second carbon is where the carboxylic acid functional group needs to be. So it's a double bond to a single oxygen and then a single bond to another oxygen and a hydrogen attached to create the full functional group, the COOH functional group of the carboxylic acid. There's the display formula of ethanol and of ethanoic acid shown. So question C, part C, is about ethanol and how it's manufactured by 2 different processes or different methods. That's the hydration of ethene versus the fermentation of glucose. And the question is asking us to discuss the advantages and disadvantages of these 2 methods using information from the table. This question is all about extracting information from the table and presenting it in a cogent and coherent argument. I break it into pieces if I were you. So let's have a look at my argument regarding the advantages of fermentation first of all. First of all, the fermentation involves the use of sugarcane crop, which is a renewable resource. Okay, it's a highly sustainable resource and it isn't a finite resource like, for example, crude oil. Now, next, yeast is not a particularly dangerous or harmful byproduct or waste product of the process. It's just a biological material. And finally, low temperatures and pressures are required. 30 degrees centigrade and 1 atmospheric pressure. These are low temperatures and low pressures. The operating costs and therefore the energy requirements will be lowered, and that's going to reduce the cost of the process as a whole. On the other hand, the disadvantages are that the fermentation of to produce ethanol is a reasonably slow process. It's a batch process. You've got to harvest the crops, you've got to process them, you've got to wait for the crops to grow again. This is going to be a really slow and laborious process in that respect. Ethanol produced at the end also won't be a pure singular product. It'll be mixed with various other things like the excess yeast, the various biological matter from the plants, and that will have to be separated, which adds extra stages. And finally, sugarcane is not being used as a food product or a food stock, and that's consideration, particularly if you're talking about an LEDC country, a low economic developed country, where maybe food is a priority. It might not be prudent, shall we say, to use that sugarcane for the production of ethanol rather than as a foodstuff. Now, in terms of hydration of ethene, its advantages are it's far faster and it's a continuous process running 24/7, and it's going to produce a pure ethanol at the end, just ethanol as the only singular product, and give you therefore a higher yield than the fermentation process would be able to produce. On the other hand, though, there are some disadvantages to the hydration of ethene, including the fact we're using a concentrated phosphoric acid catalyst, which is a corrosive waste product, and we need more consideration in terms of how we're going to deal with that. The higher temperature and pressures required will increase the cost of the process. And finally, we're using ethene derived from crude oil as the main feedstock chemical, and that's going to deplete this non-renewable finite resource pretty rapidly over time. Now, the final part of the question was looking at a word equation for they were given a word equation for the process of fermentation, had to generate a balanced symbol equation. So initially we had just drawn out the formula of ethanol and carbon dioxide, and you can see there that gives us 3 carbons, but actually there are 6 carbons coming from the glucose molecules. So if we multiplied the if we put a coefficient 2 in front of the ethanol, multiplying that up by 2, that would give us 2 times 2, which is 4, plus 1, which is 5 carbons, almost there. And if we also multiply the carbon dioxide by 2, that gives us 2 times 2, which is 4, plus 2, which is 6. 6 carbons matching the glucose molecules, and it also matches for hydrogens and oxygens as well. That would be our balanced equation. Okay, so question 6, the dreaded electrolysis question. Here we've been given a diagram of setup for the electrolysis of sodium chloride solution. Okay, we're collecting hydrogen gas and chlorine gas. Hydrogen gas at the negative cathode and chlorine gas at the positive anode. And we're now being asked to initially give a test for the presence of hydrogen gas. Okay, so that would be the squeaky pop test. But you want to describe that test. So you place a lit splint over the source of the hydrogen gas, and you should hear a squeaky pop as there's a reaction between hydrogen and oxygen, and you get a slight small explosion, which is the squeaky pop itself. Next, it says give a test for chlorine gas. And now the test for chlorine gas is you take some damp blue litmus paper, make sure the paper is damp so that it will dissolve the gas onto the surface of the paper, and it will bleach the pigmentation from the paper. It will bleach the paper to white, and that's how you test for chlorine gas. So in B, we're being asked about an ionic half equation for chlorine. We're given the ionic half equation for chlorine is two chloride ions, 2 Cl minus, going to the positive anode, where they are losing 2 electrons to form a molecule of chlorine. We're being asked to state why this reaction is an oxidation reaction. Now, I'd be tempted to write the term oil rig down the side of the page. Oxidation is loss of electrons, reduction is the gain of electrons. And as I said earlier on, in this particular half equation, we can see that the chlorine is being formed for the loss of electrons from the chloride ions, because we've gone from a negative species to an uncharged species. We must have lost electrons to do that. So the two chloride ions have lost an electron each, forming our chlorine molecule, and that therefore is an example of an oxidation reaction, because oxidation is the loss of electrons from a species. Next, being asked to give an ionic half equation for the formation of hydrogen at the negative electrode. Okay, so we're forming hydrogen gas, which is H2 gas. So to do that, we need to have two hydrogen ions migrating towards the electrode, the negative electrode, the cathode. Once they arrive at the electrode, they're going to pick up one negative electron each to remove that positive charge. So it's two positively charged hydrogen ions arriving at the cathode, collecting one electron each, two total, to form H2 or hydrogen gas. Now, state why it is safer to do this electrolysis in a fume cupboard. Well, we've been making some chlorine gas, and hopefully remember that chlorine gas is toxic in nature, and you would not want to be breathing that in. So therefore, a well-ventilated room or a fume cupboard would be a safer way of undertaking this particular experiment. And then finally, it says, suggest why the volume of chlorine collected during this electrolysis is less than the volume of hydrogen collected. That's quite a cool question. Now, it's because of the solubility of the chlorine in the water. As you've probably come across this in swimming pools, chlorine dissolves readily in water, and that's why we use it to sterilize our water supplies and also our swimming pools. So it's likely that some of the chlorine molecules we're generating will be readily dissolving into the water around them of the solution, and therefore you won't be collecting them as effectively as you will the hydrogen, which is less soluble in the water and will be collected unimpeded by the dissolving process. So it's a really nice question, that one. The next question is looking at the electrolysis of molten sodium chloride. And it's the classic question they always ask when dealing with why we need to melt electrolytes. So it says, explain why sodium chloride needs to be molten rather than solid for electrolysis to occur. And this is an ionic compound and therefore a giant ionic structure or lattice question. So effectively, we can look at this from two angles. In the solid, we're talking about a giant ionic lattice. So the ions are being held in fixed positions by the strong ionic bonds, the strong electrostatic force of attraction between opposite charged ions, and therefore they're not moving. However, when we melt that ionic compound, we break the ionic bonds, we break or overcome the strong electrostatic force of attraction between opposite charged ions, and that means the ions are now free to move. And because they're moving charged particles, we now have the conduction of an electrical current, because moving charged particles is generating the electrical current as a result. The final question on the page is a large-scale calculation where we have to work out the volume of gas generated from a large amount of sodium chloride. So we're being asked to calculate the maximum volume in litres of chlorine gas at room temperature pressure that can be obtained from 23.4 tonnes of molten sodium chloride. We've been told that the conversion of tonnes into grams is there's 10 to the 6 or a million grams in 1 tonne. We're given the relative mass of sodium chloride is 58.5. We're told the molar volume, the amount of volume occupied by 1 mole of any gas is 24 litres, and we're being asked to present our answer in standard form. So a lot of information processing going on here. So to make things easier, the first thing I would do is to write down the two formula triangles we're going to need for this calculation. So firstly, we've got number 1 over here, which is the mass mole conversion table, or the mass mole conversion triangle, sorry. And the second one is the molar volume triangle. So the mole times 24 litres gives us the volume of gas present. So first thing we need to do is calculate how many moles there actually are in 23.4 tonnes of sodium chloride. So that's moles equals mass divided by relative mass. So we convert our mass into grams, so 23.4 tonnes times 10 to the 6 grams to convert it into grams, divided by 58.5, which is the relative mass of sodium chloride, gives us 400,000 moles worth of sodium chloride. Now we apply something called the molar ratio. Now this has come from the balanced equation. We can see in the balanced equation that if we had 2 moles worth of sodium chloride, it'll always generate 1 mole's worth of chlorine gas. So we write down that ratio of 2 to 1, and we apply it to the amount of moles of sodium chloride we actually have in our experiment. We don't have 2 moles worth of sodium chloride, we have 400,000 moles worth of sodium chloride. To get from 2 to 1 is a division of 2, so if we divide this number by 2 as well, we find we can deduce that we would produce 200,000 moles worth of chlorine if we had 400,000 moles worth of sodium chloride. Just like if we had 2, we could form 1. It's applying the same ratio to the new scenario. Now finally, we can convert that number of moles into a volume by multiplying by using this formula triangle over here. So we're going to do volume is equal to moles times 24 litres. So we're doing volume equals moles times 24. 200,000 moles worth of chlorine times by 24 decimeters cubed, the molar volume, the amount of volume occupied by 1 mole of gas, gives us 4,800,000 litres of chlorine gas being generated. Now we're being asked to present that in standard form rather than as a number, a numerical value. So standard numerical value. So to convert it into standard form, we're going to think about where we're going to place that decimal point and how many places we need to move. So for every single movement of place of the decimal, it's a tenfold increase. So that'd be 10, 100, 1,000, 10,000, 100,000, million. So that would be in standard form presenting that number as 4.8 times 10 to the 6 decimeters cubed of volume, and that completes that rather chunky calculation question. And the final question of the paper is question 7, and it is a titration question. We start off with a really nice question, which is looking at apparatus. We're given apparatus X, Y, and Z, and we have to name apparatus X, Y, and Z. Well, X is looking very familiar to us as a conical flask. Y is a 25 centimeter cube glass pipette, and Z is a burette, a very high resolution piece of apparatus. So we have a conical flask X, pipette Y, and burette as Z. Now next, what is the colour of phenolphthalein in phosphoric acid? Well, remember, phenolphthalein is a binary indicator used to test the presence of alkalis generally. So in all other conditions, be it acidity or neutrality, it will be colourless, but it turns bright pink, vibrant pink in alkali conditions. Now, because phosphoric acid is an acid, it's going to appear colourless because it's not going to be able to indicate for acidity, only for alkalinity in nature. Okay, next we're looking at a titration results table. We've got the number of titrations undertaken, and we've got the results of those titrations, and we're looking for concordant results. Now, concordant results have been told to us, that's very generous of them telling us what concordant results are, as any results within 0.2 centimeters cubed of each other. And actually, looking at the table here, there are 3 results that are within 0.2 of each other, which is 30.35, 30.25, and 30.30, which are all within 0.2 of the middle point marker, which is 30.25. So those 3 results could be classified as concordant with each other. So we tick those 3 results, and we take the average of those 3 results. So we add the 3 results together, 30.35, 30.25, and 30.30, and divide by 3, gives us the average titer value of 30.30, which we record as our mean volume from the concordant results produced. And we find ourselves on the final page of this particular paper. We're given a table of results for the volume of phosphoric acid used in centimeters cubed is 25 centimeters cubed, the concentration of sodium dioxide solution as 0.525, and the mean volume of sodium dioxide added in a second titration as 30.40. We're being asked to calculate the amount in moles of sodium hydroxide in that 30.40 centimeter cubes sample of sodium hydroxide solution. So we can see we've got both a concentration and a volume for the sodium hydroxide. So that means we're going to use the formula triangle shown here. Concentration equals moles over vols. Moles is concentration times volume, and we're trying to find the number of moles. So that would be the concentration, which is 0.525 from the table above, multiplied by the volume. Now the volume has to match up in terms of units of scale with the concentration. They're both in litres or decimeters cubed. So we have to divide this centimetre cube value of 30.40 by 1,000 to convert it from centimetres cubed into decimeters cubed. There are 1,000 centimetres cubed in 1 decimeter cubed. So it's 0.525 times 30.4 over 1,000, or the unit in decimeters, giving us a number of moles of sodium dioxide of 0.01596, which we record as our amount in the answer here. We're then being asked to calculate the amount in moles of phosphoric acid found in the 25 centimeter cubed sample in the conical flask. That's where we apply again the molar ratio. Looking at the equation, we can see that for every 3 moles of sodium hydroxide, they react predictably with 1 mole of phosphoric acid in the reaction. So it's a 3-to-1 or 1-to-3 ratio. Now we know about the 3, we know about the sodium hydroxide. We're trying to find out about the phosphoric acid, which is the 1 in this ratio. So it's a 3-to-1 ratio, and to get from 3 to 1 is the division of 3. So if you take the actual amount of moles we have in our experiment and apply the same ratio and therefore divide by 3, we find out that 0.01596 moles worth of sodium hydroxide is going to be able to react with
5.32 times 10 to the minus 3 moles worth of phosphoric acid, and that's our answer here. So it's a 3-to-1 ratio of sodium hydroxide to phosphoric acid. The final part of the question says calculate the concentration in moles per litre of that phosphoric acid. Again, applying our formula triangle, moles, concentration, volume. Concentration was moles over volume, so that would be the number of moles divided by the volume of the phosphoric acid, again converted into litres or decimeters cubed. So 25 over 1,000 to convert the centimeters cube value into decimeters cube value. So 5.32 times 10 to the minus 3 divided by 0.025 equals 0.2128 moles per litre, which is the eventual concentration of our phosphoric acid. And they've broken this titration calculation into 3 manageable steps. And that is the conclusion of this 100% walkthrough of the 2021 Paper 2 IGCSE Chemistry paper. And I wish you guys all the best of luck in your endeavours in chemistry in the future. Thanks for listening. Take care. Bye for now.